Section 1. Why do cosmetics need dispersants? Have you ever shaken a sunscreen bottle and still found white residue at the bottom? Or applied a foundation that came out patchy and uneven? That's dispersion failure. Cosmetics are packed with insoluble particles. TO2 and ZNO nanoparticles in sunscreen, mica, and iron oxide pigments in foundation, color powders in lipstick, and oil droplets in moisturizers. Left untreated, van der Waals forces pull these particles together, causing aggregation, sedimentation, and product failure. Without a dispersant, particles clump and sink. With a polymeric dispersant, they stay uniformly suspended. And the difference isn't just visual. Aggregated TO2 particles in sunscreen can cause the real SPF to drop well below what's printed on the label. Section 2. The structural design of polymeric dispersants. The design logic is simple but powerful. Anchor group appears on particle surface. One end, called the anchor group, grabs tightly onto the particle surface. Through hydrogen bonding or electrostatic interactions, stabilizing chain extends into solution. The other end, the stabilizing chain, stretches out into the surrounding solution, creating a physical or electrical barrier that keeps other particles at a safe distance. The first structural type is the cone copolymer. Picture a backbone lying flat on the particle surface, with rows of PEG hydrophilic side chains grafted along it. Like a molecular brush. The multiple attachment points make it extremely hard to detach, and the uniform brush layer provides strong steric stabilization. The second type is the block copolymer. Two distinct segments in one molecule. The red segment anchors onto the particle. The green segment stabilizes in solution. The structure is well defined, which means it can be precisely engineered using controlled polymerization methods like ATRP or RAFT. Chain length matters too. Too short, not enough barrier, particles can still approach. Too long, the chain folds back onto itself and loses its function. The sweet spot is roughly 5,000 to 25,000 grams per mole. To recap, three main structural types, cone, block, and graft copolymers, each suited for different particle surfaces and formulation needs. Section 3. Adsorption mechanisms. The first mechanism is electrostatic stabilization. The dispersant gives each particle a net surface charge, so they repel each other through Coulombic repulsion. The key metric is zeta potential. When the absolute value exceeds 30 millivolts, the system is stable. The downside? It's sensitive to salt and pH. Sweat alone can break it down. So it works best for rinse-off products like cleansers. The second is steric stabilization. Polymer chains form a dense brush layer around each particle. When two particles get close, the brush layers overlap. That compresses the chains, reduces entropy, and generates a strong repulsive force. This mechanism is much more tolerant of salt and pH changes, making it ideal for leave-on products like sunscreen and foundation. The third combines both. Electrosteric stabilization. Charged polymer chains provide electrical repulsion on one side, and steric barriers on the other. Dual protection, widest stability range. And it's the design found in most modern cosmetic formulations. A quick comparison. Electrostatic works in water but is fragile, steric is robust and works anywhere, and electrosteric gives you the best of both worlds. Section 4. Bio-based dispersants. Traditional dispersants are petroleum-derived. Hard to biodegrade, high carbon footprint, and potential skin irritation concerns. Driven by EU cosmetic regulations and the growing clean beauty movement, the industry is shifting toward bio-based alternatives. Biodegradable, lower carbon, and skin-friendly. First, cellulose derivatives, like HEC and CMC. Sourced from plant cell walls, one of the most abundant biomaterials on Earth. They work double duty, thickening the formula while stabilizing dispersed particles. You'll find them in cleansers and lotion bases. Second, chitosan, derived from shrimp and crab shell waste. In acidic conditions, it carries a positive charge, allowing it to anchor electrostatically onto negatively charged particle surfaces. What makes it especially useful is its natural antimicrobial activity. It can reduce the need for synthetic preservatives, which aligns perfectly with clean beauty. Third, lignosulfonate, recovered from paper mill wastewater. The sulfonate groups carry a strong negative charge, giving excellent electrostatic stabilization. It's the most circular economy-friendly option of the three. The main limitation is its dark brown color, which restricts its use in clear or light-colored products. All three come from renewable or waste sources, each with its own strength. Cellulose for cost and abundance, chitosan for multifunctionality, and lignosulfonate for circular economy impact. Section 5. Real-world applications in cosmetics. In sunscreen, TO2 nanoparticles need steric or electrosteric stabilization, because the formula must withstand sweat, which is both salty and slightly acidic. When particles stay nano-sized, they scatter UV light efficiently and deliver the SPF on the label. Let them aggregate, and the actual SPF drops. Bio-based options include HEC for the water phase and modified chitosan as a secondary stabilizer. Foundation pigments, mica flakes, and iron oxides work best with cone copolymers. Multi-point anchoring gives long-term stability, and the uniform brush layer ensures even color payoff and a smooth feel on skin. Soy peptides are an emerging bio-based option here. For emulsions and moisturizers, the challenge is stabilizing the oil-water interface. One of the most exciting recent developments is the Pickering emulsion concept. Instead of surfactants, solid chitosan nanoparticles physically lock the interface in place. More stable, more resistant to electrolytes, and gentler on skin when bio-based particles are used. So to bring it all together, structural design, the right adsorption mechanism, and bio-based sustainable materials are working together to push cosmetics toward products that are more effective, safer, and kinder to the planet. Thank you.